I've got the record on. Here, Joshua. I've got the record on, and so we're going to go ahead and get started. We had started defining capacitance on Wednesday, and then I decided that I didn't want to jump into this because it takes a little bit. And it's a good thing because I think I've had 3 people email me with questions about this. So I was like, okay, well, we're going to cover it in class on Friday, so hang on there because it's a little complicated to try and send it to you in words in an email. Because it's one of those things that we have to look at a couple of different aspects. So most of you have done this. I'm going to go ahead and switch over to the document camera if everything works, which in and of itself is sometimes. It's thinking about it. It's still thinking about it. Yay! Looks like you guys can see the document camera over there, and you can see it over here. So let's start with what's the difference between parallel and series. Because this is going to become important for a lot of different aspects of what we're about to do in circuits. And for whatever reason, and I blame it on Radio Shack, because Radio Shack disappeared, and people don't play with circuit kits anymore, and we can't just run down to Radio Shack to find resistors and stuff like that. So we don't get a chance to play with circuits, and we don't get a chance to really look at it. And from a practical aspect, you don't really think about it, but if you're working on your house doing any kind of remodels or anything like that, a lot of times you're going to have to change out your outlets. And if you've got outlets, and if you're putting in a ceiling fan with double switches, or you're putting in an outlet that has a light switch in it, or some outlet, some light switches, control outlets, all of those things deal with series and parallel circuits and how those circuits are put together. So let's look at what we mean by series. And your Christmas tree lighting does the same thing. If you're doing your lights on your Christmas tree. So if I'm drawing a circuit and I start with a switch, okay? I start with a switch. I can put a device, whether that's a capacitor or a resistor or an inductor or a diode or any kind of device. And if I put that device there and I put this device here, and then we come through and draw our circuit, this is a circuit that's in series. And if you think about my little positive charge, my positive charge has to travel through here, go through this device, go through that device, and then comes around my circuit. So in series means I've got to do step 1, step 2, step 3, step 4, step 5, step 6, and it's going to travel through the device just like that. Now when I'm in parallel, it's a little different. So if I'm in parallel, what happens is I have a device, whether it's my capacitor, my resistor, something like that. I have a device, and it goes through like this. So when my charge comes through here, it's going to get to a point, and it gets to make a choice. It can either go through this device, or it can go through that device. So if I think about my Christmas tree lights, most of us, now we get the new little lights, and if one of the little lights burns out, the rest of the lights stay on, right? If I buy a fresh one. But most of us have, or know of an old string of lights where if one of them burns out, the other ones all go out. Because if I'm doing that and I'm in series, if this device doesn't function, I don't get flow in my circuit. So if you think about those old-timey Christmas lights, one of the bulbs was removed or it was burned out, I essentially had an open switch. Now, over here, the way they wire Christmas lights now, if this one's burned out, the circuit doesn't care because it can go through the other device. So this one is in parallel. So, and I know from experience, I know from experience, when you guys are done this in the lab, you get confused between series and parallel. And it really isn't that complicated until you get to the circuit boards, because then it's just trying to follow where when you've done it with resistors or capacitors, when you've got all the banana strings, that's kind of easy because you can set this up. You can, I'm going to set my little resistors in a ladder and have the wires go from here to here, here to here, and you can do it. But when you do it on the circuit board, I don't think you guys haven't done one with the circuit board yet, have you? In the lab, you've only done just with the free resistors. Yeah. When you guys get to the circuit boards, it's a little more complicated, because what happens on your circuit board is you end up with, you'll get a pin with the switch, and so you're going to have to connect it to another pin, and then you've got your device here, and so it's just a little bit more complicated because everything's so grouped together on my board. So I'm going to have like resistors, I'll have capacitors, and I just have to make sure I'm connecting those things so that I can set them up in parallel and in series. And it's just, you have to kind of think through, follow the charge, okay? Follow the charge. When I'm in parallel, the charge is going to have an option. It's going to have a fork in the stream, so to speak. And when I'm in series, it's got to go through one device before it goes to the next device. So hopefully that's going to make things make a little bit more sense when we start looking at these things. So let's look at our capacitors. And we talked about this on Wednesday, that my capacitors actually store charge. So I'm going to draw a circuit. So I've got some voltage source. We talked about that this is my symbol for a capacitor. So I have two capacitors. Okay? And this circuit is in parallel because I have choices. Now my voltage source is going to be a source of charge. And when I close the circuit, that charge is going to go fill those two capacitors. So whatever charge I start with, which we're going to start with a total charge, is going to equal whatever charge is on the first capacitor and whatever charge is on the second capacitor. So we're going to call this 1, and we're going to call this 2. And if I send the charge this way, because remember we talk about a positive charge, that means that this side is positive, this side is positive, this side is negative, that side is negative. And we also talked about that there's going to be a little bit of a time delay, because it's going to take a little time for these capacitors to fill. So I'm going to get a little bit of charge delay. Now, remember we also showed on Wednesday that charge is equal to my capacitance, whatever my capacitance is, times my change in voltage, or my potential, whatever this potential is. So if I rearrange this, okay, I'm going to have my total charge is going to equal whatever the capacitance is on charge 1 times my change in potential, and whatever my charge is on 2 times my change in potential. And if I look at this here, I can call this my equivalent capacitance for my system times my change in potential for the whole system. That's this right here, right? For the whole system. Well, it turns out that when I have a system in parallel, again, because I could break this one, right? And the system would still work. So if I broke this one, the change in potential is equal to the change in potential that I have right here. If I break this one, the change in potential is the same change in potential. So it turns out that my change in potential doesn't matter whether I'm in 1 or in 2, it's all the same. It's totally all the same. So I can rewrite this as 1 change in potential plus 2 change in potential. And so if that's all the same, I can cancel these out on both sides. I can factor them out and cancel them out. And my equivalent capacitance is just going to be the sum of the two capacitors that I have in the system. And if I put in 3, 4, 5, 6, 7, doesn't matter, as long as they're in parallel, my equivalent capacitance is going to equal that right there. It's not going to change. Okay? So this is for parallel. And I'm going to warn you when we get to resistors, because you guys probably already found out in the lab, capacitors and resistors are flip-flopped. So we're going to look at it in series. So this time, I've got my voltage source. I have a capacitor 1, I have a capacitor 2, and I've got my circuit. Now, this time, the charge is going to do something different. Okay? The charge is going to be, whatever the charge is in the system, it's going to stay in the system. And if I were to take my voltmeter and measure from here to here, that's my change in voltage. But I've got two devices between it. And it turns out that this time my change in potential is equal to the potential across the first one plus the potential across the second one. So if I measure this across here and I measure this across here, I add those two together and I should equal this. And you probably did this in the lab. Okay? This makes more sense when you've actually done it in the lab. Alright, but we still can go back and look at this, right? So let's change that. So my change in potential is equal to my charge over whatever the capacitance is. Okay? My charge, whatever the capacitance is. So in this case, what happens now is I'm going to get my charge on the system. So this is going to be charge total. This is going to be my equivalent capacitance for the system. And this is going to be the charge on 1, capacitance 1, plus the charge on 2, capacitance 2. But when we have a system in series, it's going to equilibrate. Okay? It's going to equilibrate. The charge here is going to equal the charge here. And it gets spread throughout the system. So what ultimately happens is that we get Q CEQ is equal to 1 over C1, or Q, plus Q over C2. These cancel, and I get 1 over CEQ is equal to 1 over C1 plus 1 over C2. Excuse me. if I have, and so when you guys are getting ready to have your test is going to be on March 13th, you know, we've got that coming up, you're going to be asked to calculate the equivalent capacitance for systems. You're going to want to have on your cheat sheet that CEQ is equal to C1 plus C2 plus that, however many capacitors are there for systems that are in parallel. And you're going to want 1 CEQ is equal to 1 over C1 plus 1 over C2 plus that for when I'm in series. Alright, so let's calculate equivalent capacitance for a system. Okay? So I'm going to do a quick one. I'm going to do this. I'm going to be a little complicated. And these are all going to be in farads, and I'm making these numbers up right now just so you can see this, because this is where I think people were asking me the question over the email. So if I'm going to say that this is 3 farads, this is 6 farads, this is 10 farads, and this is 5 farads. So I'm just making up numbers. First thing that we're going to do, I brought my calculator, life is good. When you do these systems, first thing you want to do is identify whether or not they're in series and parallel. And we're going to do this whole system. And you can break it up in steps. So this is in parallel, and this is in parallel. So let's find the CEQ for this one and the CEQ for that one. If I'm in parallel, I just add them together. So 6 plus 3 is 9, so this is going to be 9 farads. 10 plus 5 is 15, so this is going to be 15 farads. And then I can redraw my circuit. Okay, I redraw my circuit, and now I've got a capacitor, This one is 9 farads, this one's 15 farads. And now I can do the calculation for the other. So this is 1 CEQ is equal to 1 over 9 plus 1 over 15. All right, I can do it a couple of ways, right? I can find the common denominator, so let's do it that way just for grins and giggles. This is going to be 15, because this is going to be 9 15ths. 9 times 15 at the bottom, plus 9 at the top. This is going to give me 24, 9 times 15. Not doing that one in my head. Not on a Friday morning. This is 135. And this is equal to 1 over CEQ. The most common mistake when you guys are doing these problems, so let's go ahead and calculate this real quick. 24 divided by 135 is equal to 0.178, and that's going to be, okay, 0.178, and this is 1 over farads. Your most common mistake is you plug in this number into WebAssign, and WebAssign says you're wrong. And you are. Because it's asking you for CEQ, which is 135 divided by 24. Which is 5.625 farads. The most common mistake doing these problems is you forget that the thing you're solving for is in the denominator. You go through all of it, you've done everything right, but you forget to flip it over at the end. So you gotta watch that, okay? You gotta watch that. The other things that tend to happen, okay? So let's do a more complicated circuit. Let's see if I can come up with a more complicated circuit in my head real quick. So I'm gonna go in here and I'm gonna set up one, this is going to be 3, this is going to be 3, this is going to be 3, we'll make that 6, make this 10, make this 5, make this 2, make this 1, make this 6. And we want to know the equivalent capacitance for the system. And they're all in farads. Okay. First thing you got to do is figure out which ones are in series and which ones are in parallel. Okay? These two are in series. So I'm going to do those first. So I've got 1 over CEQ is equal to 1 over 2 plus 1 over 1, which is going to equal 1 plus 2 over 2, which is going to equal 3 halves, if I've done my arithmetic correctly. So CEQ is going to be 3 halves. So this is now 3 halves. Now I'm going to go ahead and do my things that are in parallel. So that's parallel, this is parallel. So this is 3 halves plus 6. And if I do that, it should be 1.5, right? 3 halves is 1.5. This is 7.5. This is 16. This is 9. Now, because it's getting messy, I'm going to take the step of redrawing my circuit. And when you're doing your homework, this is a good idea. Because now my system looks like this. So this is 9, this is 5, this one is 7.5, and this one is 16. But these are in series. So this is going to be 1 over CEQ is equal to 1 over 16 plus 1 over 7.5. And you can choose to do it, punch it into the calculator, which is what I'm going to do this time, just to do it as a little different. This gives me a number of 0.196. So CEQ is equal to 5.11. We can do this one. This one is 1 over CEQ is equal to 1 over 9 plus 1 over 5. That equals 0.311, so CEQ is equal to 3.21. These are now in parallel, so I can just add for the system is equal to 3.21 plus 5.11 is equal to 8.32. So for those of you who've been tackling the problem, does this make a little more sense? Because I got emails from at least 3 of you. You're all dead quiet over there. So my guess the mistakes that you might have been making in the problem. The first one is most likely like this. Because that's something we're not used to doing. We're not using to solve the problem for the inverse. It's just something that's just not used to what we're doing. And we have to take one more step. The second place that people tend to make mistakes is switching which one's parallel and which one is series. And it's going to get, and I'm going to warn you up front, because next week we're going to start talking resistors, and resistors turns out that resistors in series is going to be Req is equal to R1 plus R2, and resistors in parallel is going to be the other way. Which you guys already found out in the lab. And it's like, okay, so get me myself confused. So that's one of the reasons I give you a cheat sheet, so you can help keep yourself not getting confused. Because resistors are going to do something a little different than doing them in parallel, or doing them in circuits. Okay, so that making sense? All right. So hopefully, if that didn't answer your question, for those of you who've emailed me, let me know, and we'll see what we can do there. But I knew this was one that if I tried to write it out in a paragraph, it gets a little weird, and it may not necessarily make complete sense. Let me see what I got here. Okay, we've got some more of those kinds of things, so let's do some more of those types of problems. And then let's do a couple others. I did post on Blackboard. I posted, I opened up week 8, so week 8's got the resistor stuff in there, and there's a quick PBS series. It's called Crash Course. Don't know if you're familiar with it or not. And I put the one up on electric potential, capacitors, and I've got several of those set up in when we start to do resistors. It's kind of nice because they've got some good animations and some good graphics associated with it that makes it a little clearer. So one other thing that we have to cover is the energy stored in a capacitor. And we all know that, so what I talked about on Wednesday, one of the common capacitors is the electronic flash in a camera. That's a common capacitor. Does anybody know another big common capacitor that people are familiar with? Think about it. A lot of you are pre-med. It's a device. They carry it on ambulances. They have them in,
Defibrillator.
Defibrillator. Defibrillator is a big capacitor. So what happens when they flip the switch, they have to let it charge, right? They keep the battery, we have to charge it. And so what we want to look for is the energy stored. Because that's what we're going to do. We're going to discharge that energy through that muscle, the heart muscle. So there's an old joke out there was the one who developed us, depending on what your religious denomination is. But the thing is however, are we designed by an electrical engineer? Are we designed by a mechanical engineer? Are we designed by an environmental engineer? You can actually look at it, a structural engineer, you can look at it a number of different ways. Because if you think about it, the brain, the heart, and the muscles, all that's done by electrical signals. You know, we're a bunch of levers and pulleys to, you know, the way the muscles all work. So you've got a lot, you know, and there's a lot of fluid flow, right? So that's, you know, a lot of mechanics. So there's lots of interesting things, and there's a whole field on medical physics because we look at that part of it. So we do have energy stored. And the energy stored in the capacitor, if we look at it, we know that the change in work is going to equal our change in voltage, and we've got our change in charge. Okay? And what happens is work, which is, remember, work is related to energy, is going to be 1/2 the charge times my change in potential. We can play with these equations and rewrite it as 1/2 the capacitance times the change in potential squared. And we can rewrite this as the charge squared divided by 2 times the capacitance. So depending upon what the question asks will depend upon which form of this energy equation that you would use. Pretty straightforward. It's just that if they give you charge and potential, you want to use this one. If they give you capacitance and potential, you want to use this one. And if they give you charge and capacitance, you want to use that one. And if they give you the energy, you can figure out the charge if they give you one of the other variables. So that's our energy stored. So let's also do a real quick one. We're going to be given a parallel plate capacitor. And it's going to have an area of 4.00 times 10 to the minus 2 meters squared. It's going to have a separation of 1 times 10 to the minus 3 meters. We want to determine the capacitance, the charge on each plate, if connected to a 1.5 volt battery. We want to determine the charge density, and that's our little sigma. And we want to determine the electric field. Okay? So we're going to use a parallel plate capacitor. We're given that information, and we want to calculate a bunch of information for it. So at this point, we got to remember what we've been working with so far. So we said that capacitance was dependent upon the material. So my capacitance we defined as the permittivity of free space, the area divided by the distance. Permittivity of free space is 8.85 times 10 to the minus 12 Coulomb squared Newton meters squared. And we've got our 4 times 10 to the minus 2 meters squared. And we have our 1.0 times 10 to the minus 3 meters. We can plug that into the calculator, and that's going to give us 3.54 times 10 to the minus 10 farads. And so we will probably write it as 3.54 times 10 or to the minus 9 farads, which allows us to do through 3.54 nanofarads. 1 farad actually is a really, really big capacitor. had a mean, cruel, wicked physics teacher when I was going through my general physics. And he had a very large capacitor in the basement on the order of a farad. And he loved to have you come in and ask you, and he would hold this wire across above the contacts on the farad, or on the capacitor, and he would ask you what was going to happen when the wire touched the capacitor. It became pulverized dust with a very loud sound. And having worked in industry a long time, I will tell you snakes will vaporize if they go across a capacitor. It's not pretty. So will squirrels. Not pretty. So it can get really ugly. Capacitors are interesting. They store lots of energy. So we've determined the capacitance. Now we want to find the charge on each plate. Well, that's easy enough. My capacitance is equal to charge times my change in voltage. Capacitance times my change in voltage is going to give me my charge. We got our capacitance, which is 3.54 times 10 to the minus 10 farads. We said we had a 1.5 volt battery. And when we do that, we're going to get 5.31 times 10 to the minus 10 for my capacitance, or for my charge, coulombs. My charge density is just going to be the charge divided by the area. Well, we've got our charge now, 5.31 times 10 to the 10th coulombs divided by the area, which was 4 times 10 to the minus 2 meters squared. And that gives me 1.33 times 10 to the minus 8 coulomb meters squared. My electric field is just my change in potential divided by the distance. 1.5 divided by 1 times 10 to the minus 3. I get 1.5 times 10 to the third volt meters. So when you guys are working these problems, give yourself a second to think through what they're asking. Okay? Because 9 times out of 10, they're going to give you this huge discussion. And it's going to boil down to be one of these 3 variable problems. And you're going to trip yourself up by just reading the question. So let me give you just reading the question or thing right here. Let's do this. So we'll do a defibrillator problem. So we'll say I have a defibrillator. And it says our defibrillator has 1.2 kilojoules of energy stored in a 1.2 times 10 to the minus 4 farad capacitor. When discharged, 6.00 times 10 to the 2 joules is delivered in 2.5 milliseconds. Find the voltage needed to charge the capacitor and the average power. Okay, so that looks like a complex question. Couple things that we need to know, right? One is we got to remember what power is, right? So let's remember what power is. Power is energy over time. And guys, if it helps, because if I just did E over T, especially right now, what does that E mean to you? If I just wrote that down on a piece of paper right now, what would you think E means? You'd think it means electric field. So if it really helps, go ahead and write out energy divided by time. So not to confuse yourself. You know, later on, after you've done 1,000 of these problems, oh yeah, I know that means energy because I wrote power down, right? But we're just now getting into electric fields, and we've been doing electric fields for the last 2 weeks. So it's easy to get yourself confused. It's easy to get yourself confused. So if it helps, write out the word. And that way you won't get yourself quite so confused. So now if we do energy, and in this case we just wrote out our energy problems, right? We did energy could be one of these three. Now we wrote it out in terms of work, but work equals energy. Right? Remember work energy theorem, work equals energy. So this could be 1 over Q times change in voltage. This could be 1/2 the capacitance change in voltage squared. And it could be Q over 2C. Q squared over 2C. Alright. Well, in the problem, so let's take the black marker. In the problem, let's look at what I've got. It tells me I have some energy. It tells me I have that kind of a capacitor, so all of a sudden I can write down C is equal to 1 times 10 to the minus 4 farads. And we want the voltage needed. I need V. And I've got energy is 1.2 kilojoules, which means I have 1.2 times 10 to the third joules. So now I can say, okay, so I've got energy, and then I don't have charge, so that one's not going to work, and that one's not going to work. So now I've got energy is equal to 1/2 C change of voltage, and that's what I want to find. So this is going to be 2E divided by C, which is going to be 2 times 1.2 times 10 to the third joules, divided by 1.2 times 10 to the minus 4 farads. And now we're back to my units look ugly, right? So it's a little harder to do that. But this ends up equaling 2 times 10 to the 7 volts. So that's what's required to charge my capacitor. That's the voltage. Because this equals V squared, and then we take the square root, we get that. Wait, maybe I didn't take the square root. Hang on. We'll figure this out real quick. I may not have taken the square root. 1.2. That's 2 to the 7th. I didn't take the square root. That's v squared. So that actually is going to end up being 4472 volts, because that's voltage squared. Now, if we want to do the power part, this time we have to look at the energy delivered. So that one, we have to do that. So the power is going to be 6.00 times 10 to the second joules. And now we divide that by 2.5 times 10 to the 3 minus 3 seconds. And that's going to give me 2.4 times 10 to the 5 watts. Making sense? Do another one like that, and then we'll do some more equivalent capacitance kind of problems. Actually, we'll do a couple real quick ones. We have a 9-volt battery and a 6 microfarad capacitor. What is the charge in the system? Capacitance is equal to charge divided by volts. We want to solve for charge. Any capacity divided by volts. I'm going to do my 6 times 10 to the minus 6 times 9. Gives me 5.4 times 10 to the minus 5 coulombs. Or 54 microcoulombs. Now, WebAssign may have, look and make sure what WebAssign is asking you to punch in, because it may be asking for microcoulombs, it may be asking for picocoulombs, it may be asking for nanocoulombs or nanofarads, so that you're not having to write in the times 10 to the minus 5. So watch what WebAssign is asking for. So if our camera has a 120 microfarad capacitor, and we're going to have a 1.5 volt battery, how much energy is stored? Energy is going to equal CV squared divided by 2, or 1/2 CV squared. It's going to mean 1/2 120 times 10 to the minus 6, 1.5 squared, and that's going to equal 1.35 times 10 to the minus 4 joules. going to give you a system that looks like this. This is a 9-volt battery. This is a 4 microfarad capacitor. This is a 2 microfarad capacitor. And this is a 1 microfarad capacitor. We want to find the equivalent capacitance of the system. We want to find the charge on each. And we want to find the voltage on each. Okay, so this is where things get a little tricky. You have to really kind of look at your system. So let's look at the system here. Those are in parallel. So if those are in parallel, 1 plus 2 is equal to 3. And that's going to be microfarads. So now I can redraw my system. So this is 4, and that's 3, and that's 9 volts. So now I got to do the 1 over CEQ is equal to 1 over 3 plus 1 over 4. That's going to be 4 plus 3 divided by 12. So CEQ is going to be 12 divided by 7, which is 1.7. And that's in microfarads. Okay, so the charge on each capacitor, so I'm going to write it out. The charge on each capacitor is the same as the equivalent. If I'm spelling things correctly today. So Q is just going to be CV, but this is CEQ. So that's going to be 1.7 microfarads times 9 volts okay, so if I want to do this, I'm going to end up with, this is going to end up in microcoulombs, just so that you're keeping track, so you don't necessarily have to punch things in. And that's going to give me 15.3 microcoulombs. Now that I know the charge on each, the voltage on each is going to equal the charge divided by its capacitance. Well, that's going to be 15.3 microcoulombs divided by 4. And then I can do the other. I get my 15.3 divided by 4. And then once you get that, when I'm in parallel, the charge on this one is going to equal the capacitance times my delta V, and that's going to be roughly, this one works out to be like 5, it's going to have a magnitude of 5.14 sort of, and then you just put that in to that right there. kind of have to do step by step, but you can work through it. So I'm going to ask the question, you want me to work? I've got a couple more that I can work to find equivalent capacitance of the systems. You want me to work a couple more? I've got nodding, everybody's ready to just go to the next class. Okay. All right. We'll start resistors on Wednesday. This covers